Welcome to the Bodhi Academy. My name is Amsha Plaso, and in today's video we'll continue with our class 11 chapter 5 Thermodynamics. Now in today's video we will learn about some of the state functions that are very useful to us. To begin with, let's talk about the enthalpy, that is denoted by the alphabet H. Now we know that the heat that is absorbed at constant volume is equal to the change in the internal energy. So here we know that what we are saying, delta U equals to the heat energy, internal heat energy that is being absorbed. Okay, so that is QV at constant volume. Q is the heat and V denotes here the constant volume. But most of the chemical reactions are carried out not at constant volume but in flasks or test tubes under constant atmospheric pressure. So now what we are saying, that this relation is there, but when we are doing it experimentally, what is happening, that we are not considering the volume to be constant. Instead, we are considering the atmospheric pressure to be constant. Now we need to define other state functions which may be suitable for these conditions. So we may write the equation that is as delta Q equals to W plus, so this was here, this 5.1 equation was delta U equals to Q plus W, heat and work done. So now here we are substituting this work done as minus delta P delta V. Now over here we have taken this heat absorbed at constant pressure, where QP is the heat absorbed by the system and minus P delta V represents the expansion work that is done by the system. Now let us represent the initial state of the state by subscript 1 and final state by subscript 2. So here we are now going to define these change. So this we have taken as minus P delta V, right? So now this we are going to divide as U2 minus U1 equals to Q minus P. Delta V will be again V2 minus V1. So this is how we are going further. Then on rearranging, so now the QP term we have taken on one side and both the U2 plus PV2. Here now we have opened up this bracket. So if you have U2 minus U1 equals to QP minus PV2 minus PV1. Now we have rearranged this. So this QP we have taken on one side and on the other side we have taken the terms with the subscript 2 together. So U2 plus PV2 and the other will be U1 plus PV1. Now we can define another thermodynamic function that is known as the enthalpy given by H, which tells us about the heat content. So now enthalpy is given by the internal energy plus PV. Okay. Now so equation 5.6, if we look at this equation and then we try to rearrange this equation. So if you see this equation, it is same as this one, correct? Only here we have substituted the initial and the final states over. So if you want to write this in the form of this enthalpy equation that is given, so we will write, this will become my whole H2 and this becomes my whole H1, because H2 is what? Q plus PV. Again H1 is also U plus PV. So we will get this a certain term. So we can write QP equals to H2 minus H1, that is equals to delta H. Now although Q is a part dependent function, H is a state function because it depends on U, P and V, all of which are state functions. Therefore we can say that delta H, it is independent of the path, and hence if delta H is independent, QP, that is heat absorbed at constant pressure, also becomes independent of the path. Now next let's look at this when we have a negative sign and when we have a positive sign for delta H. So delta H is negative when the reaction is exothermic, that is heat is evolved during this reaction, and delta H is positive, that is it is endothermic when heat is being absorbed from the surroundings. Now at constant volume, that is delta V equals to 0 and delta U equals to QV, that is heat absorbed at constant volume, we can say that delta H will be equal to delta U equals to delta V, same as the previous one. Only the difference between delta H and delta U is not usually significant for systems consisting of only one solid or one liquid. So, however, the difference that is there, it comes into significance only when number of gases are involved. So now let us consider a reaction that involves gases. Say VA is the total volume of a gas reactants, VB is the total volume of a gaseous products, Na is the number of moles of gaseous reactants, and Nb is the number of moles of the gaseous products. Now from all of this, if we consider the pressure and temperature to be constant, then using the ideal gas equations, that is PV equals to nRT, we can write separately for A, that is reactant, and B. So PVA equals to NART and PVB equals to NBRT. Now if we take out these, equate both of these equations, we finally get a relation here, that is P delta V equals to delta NG RT. Now this Ng which is over here, it basically represents the number of moles of the gaseous product minus the number of moles of the gaseous reactant. So it is the difference between the number of moles of gaseous products and number of moles of the gaseous reactants. Now substituting the value of P delta V from equation 5.9 in equation 5.8, we can get that delta H was equal to what? PV here. So now this PV, we have found a value, that is delta NGRT. So our new enthalpy equation changes to delta H equals to delta U plus delta NGRT. Now let's understand what are these extensive and intensive properties. In thermodynamics, a distinction is made between extensive properties and intensive properties. So now what are these extensive properties? So extensive property is a property whose value depends on the quantity or size of matter that is present in the system. Okay. For example, if we talk about mass, volume, internal energy, enthalpy, heat, capacity, etc. Now here what we are saying, if we talk about say volume, okay, what will happen if say I have 100 ml of water in this, okay. Now this if I divide, okay, so I have now 2 beakers of 50 ml each water. Here what will happen, the properties here will vary because why, the volume itself has changed, correct. So no matter if I take over here, when I divided this volume, this has now got into two different states, it is not like it has remained same. Now if we look at intensive properties, it is exactly the opposite of extensive properties, in that the properties, those properties which do not depend on the quantity or the size of matter that is present, these are known as intensive properties. For example, say let's talk about temperature, okay. Now say I take 20 ml of water, that is at say 60 degrees Celsius, okay. Say now from this I am removing 10 ml of water. Now will the temperature of this water be any different? No, it is still going to be 60 degrees Celsius. Now let's talk about density. If I say, okay, say I take 1 drop of water, 1 drop of water. Now the density of 1 drop of water and 5 ml of water, will it vary? No, it is going to still remain the same. So no matter how much you divide this, some of its properties are remaining same, like temperature, density, even pressure. So these are intensive properties. They do not depend on how much is present or what is the size that is present, okay. Whereas extensive properties, it definitely depends on how much is present. Now let's next talk about the heat capacity. So in this subsection, let us see how to measure heat transfer to a system. This heat appears as a rise in temperature of the system in case of heat absorbed by the system. So the increase of temperature, we are saying, is directly proportional to the heat transfer. So Q equals to C coefficient into delta T. Now the magnitude of the coefficient, it depends on the size, composition and nature of the system. So we can write that Q, that is heat, equals to C delta V. Now this C over here, this coefficient C is known as the heat capacity. So when C is large, a large amount of heat results in only a small temperature rise. Water has a large heat capacity, that is, we know that water needs a lot of energy to get its temperature reached. Now if C is directly proportional to the amount of substance, we can say that the molar heat capacity of a substance Cm tells us that it is molar heat capacity equals to C upon N, is the heat capacity for 1 mole of substance and is the quantity of heat needed to rise the temperature by 1 mole by temperature of 1 mole by 1 degree Celsius. So molar heat capacity, it is what? It is the heat capacity for 1 mole of substance and is the quantity of heat that is required to raise the temperature of 1 mole by 1 degree Celsius. Now same as molar heat capacity, we also have something known as the specific heat capacity. Now this is the amount of heat that is required to raise the temperature of 1 unit of mass by 1 degree. Here we are talking in terms of mole and here we are talking in terms of 1 unit mass. So for finding out the heat required to raise the temperature of a sample, we simply multiply the specific heat of the substance C by the mass M and the temperatures delta T as Q equals to C into M into delta T, that equals to C delta T. Now let us understand what is the relation between Cp and Cv for an ideal gas. Before that, C we already know is the heat capacity. When we have a subscript P, it means that it is the heat capacity at constant pressure, and Cv, this is at constant pressure, and this Cv is at constant temperature. Okay, so Cv is the Cp is the heat capacity at constant pressure and Cv is the heat capacity at constant, sorry, this is volume, Cv. Now let us find what is the relation between these two quantities that are given here. So we can write at constant volume QV, that is heat at constant volume, will be equal to Cv delta T. Now the Cv delta T in 10 equals to the internal energy, that is delta U. So now if we look at constant pressure, that is Qp equals to, it will be Cp delta T. Again Cp delta T equals to delta H, that is the enthalpy. Now if we want to find the difference between Cp and Cv, we can derive it from using the ideal gas equation. So for 1 mole of an ideal gas, delta H equals to delta U plus delta PV. Okay, now this PV, if we know from the ideal gas equation itself, PV equals to nRT. So here if we consider this N as 1, we know that it is PV equals to RT. So that you have to substitute over here. Okay, so then delta U will be equal to delta RT. Now if we open up this bracket, we'll have delta U equals to R delta T. So delta H will be in short equals to delta U plus R delta T. Now if we already know the values of these two, delta H and delta U, if we directly substitute them in the given formula, that is Cp for delta H, it is Cp delta T equals to Cv delta T plus R delta T. From here this temperature thing we can take out and we will have Cp equals to Cv plus R. Now if I want to find the difference, you take this quantity over here. So we'll have Cp minus Cv equals to R. So basically Cp, the difference between Cp and Cv gives us the R value, that is the gas constant. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Boti Academy.